Welcome back to Mysterious Sleepy History. Tonight, we're leaving the familiar world behind and traveling somewhere much farther away, into the darkness of space. Tonight, we'll be talking about black holes, the mysterious places where gravity becomes so powerful that even light cannot escape. We'll slowly follow the story of how these strange objects were first imagined, how we eventually discovered that they truly exist, and what happens when a star reaches the end of its life and collapses into darkness. And as our journey takes us closer to one of these cosmic giants, we'll wonder about something even stranger. What would it feel like to cross a boundary from which nothing can ever return? And if there is truly no escape, what happens to everything that disappears beyond it? So tonight, you don't need to search for answers or follow every detail. Just let the story unfold slowly around you. And before we begin, if you enjoy spending these quiet nights with us, take a moment to like the video and subscribe. It helps our little group grow and brings more night travelers into our community. And if you'd like, tell me in the comments where in the world you're listening from tonight and what your local time is. It's comforting to know that somewhere out there, people are sharing the same quiet journey together. So make yourself comfortable. Let your eyes grow heavy and allow the stars to slowly appear in your imagination. I'll be your night companion tonight as we travel toward a place where the darkness has no edge and where there is truly no escape. When we look into the night sky, most of what we see is connected to light. Stars shine, planets reflect light, distant galaxies send their ancient glow across enormous distances until it finally reaches us. But there are places in the universe where light never makes the journey back to us. Black holes are among the strangest of these places. The name itself can be a little misleading. A black hole is not an actual hole punched through space. It is not an empty tunnel leading somewhere else. And it is not a giant cosmic vacuum cleaner moving through the universe and swallowing everything around it. A black hole is a region of space where an enormous amount of matter has been compressed into an extremely small area. The result is an incredibly strong gravitational field that changes the shape of space and time around it. To understand this a little more easily, we can begin with something familiar: gravity. The Earth has gravity because it has mass. That gravity keeps us on the ground and keeps the moon in orbit around our planet. The sun has much more mass, so its gravity is strong enough to keep the planets moving around it. But imagine taking a huge amount of matter and squeezing it into a much smaller space. The closer that matter becomes concentrated, the stronger the gravitational effects near it become. A massive star can spend millions of years in a delicate balance. Gravity constantly pulls the star inward. At the same time, the energy produced inside the star pushes outward. For a long time, these two forces balance each other. The star remains stable. It shines quietly in the darkness. But some stars are born with so much mass that their final moments can be very different. When such a star eventually runs out of fuel, the balance begins to disappear. Gravity takes over. The star can collapse under its own enormous weight. If the remaining core is massive enough, the collapse can continue until space-time becomes extremely curved. Eventually, a boundary can form around the collapsing object. This boundary is called the event horizon. The event horizon is one of the most important ideas in understanding a black hole. It is not a solid surface. There is no wall there. There is nothing that an astronaut would physically crash into. Instead, it is a boundary in space-time. Beyond this boundary, every possible path leads deeper into the black hole. Even light has no path that can take it back out. That is why the black hole appears black. It is not because some mysterious substance absorbs all the light. It is because the light cannot escape once it passes beyond the event horizon. And this gives us a simple way to think about a black hole. It is a place where gravity has become so extreme that there is no longer a path back to the outside universe. But there is something especially fascinating about this. We cannot see the black hole itself. We cannot simply point a telescope at the darkness and photograph the object hiding inside. Instead, we look for its effects. We watch nearby stars. We study glowing gas. We observe the way light bends around it. We measure the movement of objects that seem to be orbiting something invisible. In other words, sometimes the best way to find something you cannot see is to watch what everything around it is doing. And that idea takes us back more than a century. Because long before astronomers had evidence that black holes were actually hiding in the universe, physicists had already begun to imagine them. The story of black holes begins not with a telescope, but with mathematics. In 1915, Albert Einstein introduced his general theory of relativity. It changed the way scientists understood gravity. Before Einstein, gravity was generally imagined as a force acting between objects. Einstein offered a deeper picture. Space and time were connected. Together, they formed something we now call spacetime. Mass and energy could curve this spacetime, and objects moving through that curved spacetime would follow paths that appeared to us as gravitational motion. The idea was difficult to imagine, but it gave scientists a new way to understand the universe. And almost immediately, an extraordinary possibility appeared. What would happen if an enormous amount of mass were compressed into a very small region? Could spacetime become curved so strongly that light itself would be unable to escape? In 1916, the German physicist Karl Schwarzschild found a mathematical solution to Einstein's equations that described exactly this kind of extreme object. The idea was extraordinary. A sufficiently massive object could be compressed inside a certain radius. Once this happened, something very strange would occur. The escape speed from the surface would become greater than the speed of light. Since nothing can travel faster than light, there would be no way for anything to escape. At the time, this seemed almost impossible to believe. Stars were known. Planets were known. The idea of a completely dark object whose presence could only be detected through gravity was far more mysterious. For decades, scientists debated whether such objects could really exist in nature. Perhaps they were simply strange mathematical possibilities. Perhaps real stars could never become compact enough. But the universe had other plans. As astronomy improved, scientists began finding objects that behaved exactly as though something massive and invisible was hiding nearby. A star would move through space in a strange orbit. A cloud of gas would spin around an apparently empty region. X-rays would pour out from an area where no ordinary star could be seen. Slowly, the evidence began to build. The invisible objects predicted by the mathematics were beginning to reveal themselves. Not by shining, but by moving the universe around them. And that is one of the beautiful ideas in astronomy. Sometimes the universe tells us that something exists without ever showing it to us directly. A shadow can reveal an object. A wave can reveal something moving beneath the surface, and the motion of a star can reveal a hidden gravitational giant. But there was still another question. How could nature actually create something so extreme? For that, we have to follow a star through its entire life, all the way to its final night. A massive star can spend millions of years looking almost unchanged in the night sky. From Earth, it may appear to be nothing more than a small point of light. But deep inside that point, an enormous struggle is taking place. The star is constantly fighting against itself. Gravity is always trying to pull the star inward. Every part of the star has mass, and all of that mass is attracted toward the center. If gravity were left alone, the star would collapse under its own weight. But deep inside the star, something pushes back. The temperature and pressure at the center are so extreme that nuclear fusion can take place. Light elements are joined together and transformed into heavier ones, releasing enormous amounts of energy. That energy moves outward through the star and creates pressure that helps support it against gravity. For most of a massive star's life, these two forces remain in balance. Gravity pulls inward, energy pushes outward, and somewhere between those two forces, the star continues to shine. The process can last for millions of years, but no star has an endless supply of fuel. As the star ages, the material in its core changes. Hydrogen is gradually converted into helium. Later, in very massive stars, heavier and heavier elements can be produced. The star passes through different stages of its life, each one requiring higher temperatures and greater pressures. Eventually, the core reaches a point where it can no longer gain enough energy from fusion to support the star in the same way. The balance begins to fail, and this is where the final chapter begins. Gravity does not suddenly appear. It has been there all along, but now there is less energy pushing outward to resist it. The core begins to collapse. It happens incredibly quickly. The outer layers of the star can be thrown outward in one of the most powerful events known in the universe. A supernova can briefly become brighter than an entire galaxy. For a short time, the dying star can shine with an extraordinary intensity. But while the outer layers are racing outward, the heart of the star is doing something very different. It is falling inward. The core is being crushed by its own gravity. Matter that once occupied an enormous volume is forced into a region unimaginably smaller. Atoms are squeezed together. The familiar structure of matter begins to disappear. And if the remaining core is massive enough, even the forces that normally resist gravitational collapse can no longer stop it. The collapse continues. At some point, the gravitational field becomes so strong that a region forms from which nothing can escape. The event horizon appears. From the outside, this is the moment when the object becomes a black hole. But the story does not really end there. In fact, in a strange way, this is when the most mysterious part begins. The black hole itself may now be invisible, yet the space around it can become incredibly active. If another star is nearby, the black hole can pull material from it. Gas can begin to spiral inward, forming what is called an accretion disk. This disk can become unimaginably hot. As the gas moves faster and faster around the black hole, friction and compression heat it to enormous temperatures. It can release powerful radiation, including X-rays, that telescopes can detect from across the galaxy. So although the black hole itself gives off no light, its surroundings can become some of the brightest places in the universe. This creates one of the first great clues that astronomers use when searching for black holes. They look for darkness surrounded by activity. They look for stars behaving strangely. They look for hot gas moving around something they cannot see. And they look for powerful radiation coming from regions where no ordinary object seems capable of producing it. There is another important detail. Not every massive star becomes a black hole. The final result depends largely on how much mass remains in the star's core after the explosion. Some stars leave behind incredibly dense objects called neutron stars. These are already extraordinary. A neutron star can contain more mass than the Sun while being only around the size of a city. But if the remaining core is massive enough, even a neutron star cannot remain stable. Gravity wins again. The core collapses further, and a black hole is born. This means that every black hole created from a massive star has a story behind it. Before there was darkness, there was a star. Before the star collapsed, there was a long life filled with nuclear fire. And before that, there was a cloud of gas and dust slowly gathering under gravity. In that sense, a black hole is not simply an empty darkness. It is the final stage of a very long cosmic story. And somewhere in the universe tonight, stars are living through those same stages. Some are young. Some are quietly burning. Some are approaching the final part of their lives. And somewhere, perhaps at this very moment, a massive star may be collapsing and creating a new black hole. We would not necessarily know it immediately. The event may be happening thousands or millions of light years away. The light from the explosion could still be traveling toward us, and by the time we see it, the event itself may already be ancient history. This is one of the strange things about looking into space. When we look outward, we are also looking backward. The stars we see are not necessarily showing us what is happening there right now. They are showing us what happened when their light began its journey toward Earth. A star 1,000 light years away is being seen as it was 1,000 years ago. A galaxy millions of light years away is being seen millions of years in the past. And a black hole forming in a distant galaxy could already have existed for an enormous amount of time before its story finally reaches our telescopes. This brings us to another mystery. If black holes do not shine, and if we cannot see them directly, how can we possibly know where they are? The answer begins with something very simple: movement. Imagine standing in a dark room and seeing a lamp hanging from the ceiling. You cannot see what is holding it up, but you can see the lamp. Now imagine the room is completely dark and there is no lamp. Instead, you notice a small object moving in a circle around a point that appears to contain nothing. You cannot see the object at the center, but you can see the movement of everything around it. That is very similar to how astronomers began finding black holes. A black hole has gravity, and gravity affects nearby objects. So astronomers search for things that appear to be orbiting something invisible. One of the most important clues can come from a companion star. Some stars exist in pairs. Two stars can orbit one another, traveling around a shared center of gravity. If one of those stars eventually collapses into a black hole, the surviving star may continue orbiting it. From Earth, astronomers may see only one visible star, but they can carefully measure its movement. If the star appears to be orbiting an invisible object with a huge mass, scientists can calculate what that unseen companion might be. If the invisible object is too massive to be a normal star, and yet produces no visible light, a black hole becomes a strong possibility. This method has helped astronomers identify many black hole candidates. But stars are not the only things that give black holes away. Gas can reveal them too. Imagine a black hole passing close to a normal star. Its enormous gravity can begin pulling material away from that star. The gas does not usually fall straight inward. Instead, it begins to spiral around the black hole. The gas forms a rotating disk. As the material moves closer to the black hole, it moves faster and becomes hotter. The temperature can become so high that the gas begins emitting powerful X-rays. These X-rays can travel across space and eventually reach Earth. Our telescopes detect them. And once again, we are not seeing the black hole itself. We are seeing what happens around it. This is an important distinction. When astronomers say they have found a black hole, they usually do not mean that they have photographed the black hole as though it were a planet. They have found evidence that an object with the properties of a black hole must be there. The invisible object reveals itself through gravity, radiation, motion, and the bending of light. One of the most beautiful examples of this comes from gravitational lensing. Light normally travels along the paths defined by spacetime, but massive objects can bend spacetime. And when light from a distant star or galaxy passes near a massive object, its path can bend. The effect is similar to what happens when light passes through a lens. The image of the distant object can become stretched, magnified, or distorted. Astronomers can study these changes. If the invisible object causing the distortion is massive enough, its presence can sometimes be inferred even though the object itself produces no light. A black hole can therefore act like a strange cosmic lens. It hides itself while bending the light of something behind it, and sometimes the effect is dramatic. A distant star may suddenly become brighter. Its light may appear to shift, or its image may be distorted in a way that reveals an invisible mass passing in front of it. This technique is called gravitational microlensing when the effect is relatively small and temporary. It gives astronomers another way to search for objects that would otherwise remain hidden. But there is an even larger clue. Some black holes are not alone. They can exist at the centers of galaxies. Our own galaxy, the Milky Way, contains a supermassive black hole at its center. It is called Sagittarius A star. We cannot see the black hole directly, but we can observe stars orbiting the region around it. Some of these stars move at extraordinary speeds. They follow tight orbits around a point in space that emits no ordinary visible light. By carefully tracking their positions over many years, astronomers have been able to calculate the mass concentrated at the center of our galaxy. The result is enormous. A supermassive black hole with a mass of millions of suns appears to sit at the heart of the Milky Way. And yet, despite its immense mass, it is incredibly far away from us. We are not being pulled into it. The stars of our galaxy are not spiraling helplessly toward it. The Milky Way continues its slow rotation around its center. The black hole is simply one part of a much larger galactic structure. This is another important point about black holes. They are powerful, but they are not magical cosmic vacuum cleaners. If our sun were somehow replaced by a black hole with exactly the same mass, Earth would continue orbiting at roughly the same distance. The sky would become very different because there would be no sunlight. But Earth's orbit would not suddenly collapse inward. Gravity at a distance depends on mass. The strange behavior of a black hole becomes most important when you get very close to it. And that is where our journey will eventually take us, closer and closer, past the orbiting stars, past the glowing gas, past the region where light itself begins to behave strangely, toward the event horizon, the point where the universe seems to draw a final line, a line that can be crossed, but never uncrossed. And before we reach that boundary, there is one more thing we need to understand. Because if we want to know what happens when something falls into a black hole, we first need to understand how space and time behave when gravity becomes this extreme. That is where our journey becomes even stranger. There is a moment in our journey toward a black hole when the view of the universe would begin to change in ways that are difficult to imagine. Far away from the black hole, everything would seem almost ordinary. Stars would shine. Light would travel through space. Time would pass in the familiar way. But as we moved closer, the gravity would become stronger and stronger. The black hole itself would still remain invisible. What we would notice instead is the strange behavior of the space around it. Light passing nearby would begin to bend. The stars behind the black hole could appear stretched and distorted. The darkness would seem to have a shape, and somewhere within this region would be the most important boundary of all, the event horizon. The event horizon is often described as the point of no return. This is not simply a dramatic expression. It describes a real boundary in space-time. Before reaching it, an object can still turn around. A spacecraft could fire its engines and move away. A beam of light could still travel outward. But once the event horizon is crossed, there is no path that leads back to the outside universe. Not even light can escape. This can sound as though the event horizon must be a physical wall, but it is not. There is no surface waiting there. Nothing solid marks the boundary. If you were falling toward a very large black hole, you would not suddenly crash into something when you crossed the event horizon. You could pass through it without feeling a sudden impact. The strange part is not what happens to your body at that exact moment. The strange part is what happens to your future. Once you cross the event horizon, moving deeper into the black hole becomes unavoidable. It is almost as though the direction toward the center becomes as unavoidable as moving forward through time. You cannot simply choose to turn around. You cannot stop and hover at the boundary. There is no road leading back. This is why the event horizon is so important. It does not mark a place where gravity suddenly switches on. Gravity was already there. It does not mark the point where everything is instantly destroyed. That depends on the size of the black hole and the situation around it. Instead, the event horizon marks the point beyond which escape is no longer possible. Imagine a river flowing toward a waterfall. Far upstream, the current is gentle. You can swim against it. You can change direction. As you move closer to the waterfall, the current becomes stronger. Eventually, you reach a point where the water is moving so quickly that even your strongest effort cannot carry you back upstream. You may still be floating normally. You may not notice anything unusual about the water itself. But beyond that point, your journey toward the waterfall is unavoidable. The event horizon is somewhat similar. It is not a physical barrier. It is a boundary created by the extreme geometry of space-time. And this brings us to one of the strangest features of black holes. Time itself becomes part of the story. From the perspective of someone watching you from far away, your journey toward the event horizon would appear increasingly slow. The light you send back would become weaker and more stretched. Your signals would take longer to arrive. You would appear to move more and more slowly as you approach the horizon. Eventually, from the distant observer's point of view, you would seem to fade away. It might appear as though you never quite crossed the boundary, but from your own perspective, the experience would be different. Your clock would continue to tick normally. Your thoughts would continue normally. If you were falling toward a sufficiently large black hole, you could cross the event horizon in a finite amount of your own time. You would not necessarily notice the exact moment when it happened. This difference between the outside observer and the falling traveler comes from Einstein's theory of relativity. Time is not experienced identically everywhere. Gravity affects the passage of time. The stronger the gravitational field, the more pronounced the difference can become when compared with a distant observer. This is called gravitational time dilation. We already measure tiny versions of this effect in everyday technology. Satellites experience slightly different gravitational conditions than clocks on Earth's surface. Their clocks tick at different rates. The difference is small. But near a black hole, the effect can become extreme. As you approach the event horizon, the difference between your experience and the experience of someone far away can become enormous. And yet, there is something comforting in the simplicity of the idea. For you, your own clock always feels normal. 1 second still feels like 1 second. Your heartbeat does not suddenly feel frozen. The universe does not appear to stop around you. The strange slowing of time becomes apparent when comparing your clock with clocks far away from the black hole. This is one reason black holes are so fascinating. They do not simply change where things can go. They change the relationship between space and time. And the deeper we travel into this strange environment, the more important that relationship becomes. Because eventually we have to ask a much more personal question. What would actually happen to a person who fell into a black hole? Would you simply disappear? Would you survive the journey for a while? Or would the immense difference in gravity across your body begin to pull you apart? The answer depends on the kind of black hole you are approaching. And this is where the journey becomes much more physical, because the next stage has a rather unusual name: spaghettification. Imagine that you are drifting through space toward a black hole. At first, nothing dramatic happens. The black hole may appear as a dark region surrounded by distant stars. There is no giant cosmic vacuum pulling you violently from a great distance. If you are still far away, the gravitational field may not feel very different from the gravitational field around any other massive object. You continue moving forward. The black hole grows larger in your view. The surrounding stars begin to look strange as their light is bent by the enormous gravity. And eventually, the difference in gravity between different parts of your body begins to matter. This difference is called a tidal force. You experience tidal forces on Earth too. The moon's gravity pulls slightly more strongly on the side of Earth that is closer to it, and slightly less strongly on the opposite side. This difference helps create the tides in our oceans. Near a black hole, however, tidal forces can become extraordinarily powerful. Imagine your feet are closer to the black hole than your head. Your feet experience a stronger gravitational pull because they are slightly closer to the center. Your head experiences a weaker pull because it is farther away. The difference may begin as something small, but as you move closer, the difference becomes much greater. Your body would be stretched in the direction of the black hole. At the same time, it would be compressed from the sides. The result is an extreme stretching effect that physicists call spaghettification. The name sounds almost playful. The reality is not. Matter would be stretched into a long, thin shape as the difference in gravity across the object became stronger. The same effect would happen to anything that fell inward: a spacecraft, a cloud of gas, a planet, a star. Even material that originally formed a solid object could eventually be pulled apart. But there is an important detail. Not all black holes would destroy you at the same distance. The size of the black hole matters. This may seem surprising. You might expect a larger black hole to have stronger tidal forces everywhere. But near the event horizon of a very massive black hole, the change in gravity across the size of a human body can actually be much smaller than it would be near a smaller black hole. This means that if you somehow approached a supermassive black hole, you could theoretically cross the event horizon before the tidal forces became strong enough to tear you apart. You would still be in enormous danger deeper inside, but the event horizon itself would not necessarily be the place where you are stretched apart. For a smaller stellar mass black hole, the situation could be very different. The tidal forces near the event horizon could become intense enough to stretch an approaching object before or around the time it crossed the boundary. So the size of the black hole changes the experience. This is one of the strange things about black holes. The most enormous black holes can have relatively gentle event horizons, and the smaller ones can be much more violent at their edges. But regardless of the size, once you cross the event horizon, the direction toward the center becomes unavoidable. There is no engine powerful enough to simply turn around. There is no route through space that leads back outside. Every possible future path carries you deeper into the black hole. And now the meaning of time becomes even stranger. To you, falling inward could take a finite amount of time. You would not experience yourself freezing at the event horizon. You would cross it. You would continue inward. But someone far away would describe your journey differently. They would receive your signals more and more slowly. The light from your spacecraft would become increasingly redshifted. Your image would become dimmer. Eventually, your signals would become so stretched and weak that you would effectively disappear from their view. From far away, it would look as though you were fading toward the horizon. From your own perspective, however, you would continue falling. This difference is one of the clearest examples of how strange relativity becomes near a black hole. There is no single universal clock that everyone in the universe shares. Time depends on the path you take through space-time, and near a black hole, those differences become impossible to ignore. As you fall deeper, the outside universe would also begin to look increasingly distorted. Light from distant stars could be bent around the black hole. The sky might appear to curve. Some regions of the universe could become compressed into strange shapes. The black hole would act like a giant gravitational lens surrounding you. If you could somehow look back toward the universe outside, you would not simply see an ordinary night sky. You would see light that has traveled through a profoundly distorted region of space-time. The familiar universe would begin to look unfamiliar. And yet, there is a limit to what we can say with confidence. We can describe the journey using general relativity. We can calculate how light behaves. We can calculate the motion of falling objects. We can calculate the tidal forces. But eventually we reach a region where our current understanding of physics becomes incomplete. At the center of the classical black hole lies what general relativity calls a singularity. This is where the mathematics suggests that matter becomes compressed to an extreme state and space-time curvature becomes extraordinarily large. But scientists do not believe that the word singularity necessarily gives us the final answer. It may be telling us something more important. It may be telling us that our current theories have reached their limit. General relativity is extremely successful at describing gravity and large-scale structures. Quantum mechanics is extremely successful at describing the microscopic world. But inside the deepest regions of a black hole, we need both. And we do not yet have a complete theory that successfully combines them. So the true center of a black hole remains one of the deepest mysteries in modern physics. Perhaps the singularity is a real physical feature. Perhaps something else replaces it. Perhaps our understanding of space and time changes completely at those scales. We simply do not know yet. And perhaps that uncertainty is part of what makes black holes so fascinating. They are not only objects in space. They are places where our understanding of the universe is pushed to its limits. A black hole begins with the death of a star. It grows through gravity. It bends light. It changes the passage of time. It can tear matter apart. And eventually, it leads us to a region where even our best theories can no longer give us a complete answer. But there is another mystery waiting for us. If nothing can escape from beyond the event horizon, how can a black hole ever disappear? For a long time, scientists assumed that once something crossed the horizon, it was simply gone forever. Then Stephen Hawking asked a remarkable question. What happens when the strange laws of quantum physics meet the extreme gravity of a black hole? The answer would lead to one of the most surprising ideas in the entire story. Black holes may not be completely black after all. So far, we have followed a black hole from the final moments of a massive star to the formation of the event horizon. We have watched light bend around it, imagined what it might feel like to cross the boundary, and followed the strange effects of gravity on space and time. But now, our journey takes us somewhere that is much harder to describe. Beyond the event horizon, there is a region that no signal can ever return from. And because we cannot receive information from inside, we are left with a difficult question. What is actually there? According to Einstein's theory of general relativity, everything that falls beyond the event horizon continues inward toward a region called the singularity. In the simplest picture, the singularity is the place where the matter that formed the black hole has collapsed to an incredibly extreme state. The curvature of space-time becomes so large that the equations of general relativity no longer give us a sensible description of what is happening. But the word singularity can sometimes sound more certain than it really is. It does not necessarily mean that scientists have discovered a tiny point of infinite density sitting at the center of every black hole. Instead, it may be telling us that our current theory has reached its limit. This is an important distinction. When a mathematical equation produces an infinite value, scientists do not always assume that nature itself contains a literal infinity. Sometimes the infinity is a warning that the theory is missing something. Imagine having a map of a vast, unexplored country. You follow the map carefully until eventually the road disappears, and the map simply says that the region is unknown. You would not conclude that the world ends at the edge of the map. You would understand that the map is incomplete. The singularity may be something like that. General relativity gives us an extraordinarily successful description of gravity. It explains the motion of planets, the behavior of stars, the bending of light, gravitational waves, and the large-scale structure of the universe. But inside a black hole, where gravity becomes extreme and distances become incredibly small, quantum physics must also become important. And this is where modern physics reaches one of its greatest unanswered questions. We have two extraordinarily successful descriptions of nature. General relativity describes gravity and the large-scale universe. Quantum mechanics describes the behavior of matter and energy on the smallest scales. Both theories work remarkably well within their own domains, but inside a black hole, we need them to work together. We do not yet have a complete theory of quantum gravity that can fully describe this environment. So when we ask what is really inside a black hole, the honest answer is that we do not know. We have mathematical predictions. We have powerful theories. We have observations of what happens outside black holes. But we do not have direct information from beyond the event horizon. And this creates a natural limit to what science can currently tell us. Perhaps the center contains a singularity in some form. Perhaps quantum gravity prevents matter from collapsing indefinitely. Perhaps space-time itself changes character at these extreme scales. There are many ideas, but none has yet become a complete and experimentally confirmed answer. This uncertainty does not make black holes less fascinating. In many ways, it makes them more important. Black holes show us exactly where our understanding of nature begins to become incomplete. They are like natural laboratories that push physics into conditions we could never reproduce easily on Earth. And there is another important thing to understand. When people imagine a black hole, they often picture an enormous cosmic mouth swallowing everything around it. A star disappears. A planet disappears. A galaxy disappears. Everything nearby is pulled helplessly toward the darkness. But this is one of the biggest misunderstandings about black holes. Black holes do not automatically swallow everything around them. They obey gravity just like every other object with mass. The difference is that their mass has been compressed into an extremely small region. If you were far enough away from a black hole, its gravitational pull would behave in a familiar way. In fact, if the Sun were somehow replaced by a black hole with exactly the same mass, the planets would continue orbiting at almost the same distances. The Earth would not suddenly be sucked into the black hole. The planets would continue following their orbits. The biggest difference would be that there would be no sunlight. Our planet would become cold and dark, but gravitationally, the situation would be surprisingly similar. This helps us understand something important. Black holes are not cosmic vacuum cleaners. They do not travel through space looking for objects to consume. A black hole can capture something if that object gets too close or if its path carries it across the event horizon. But objects can also orbit black holes perfectly well. Stars can orbit them. Gas can orbit them. Entire groups of stars can remain in stable orbits around supermassive black holes at the centers of galaxies. Our own Milky Way is a good example. At its center is Sagittarius A star, a supermassive black hole containing millions of times the mass of our Sun. And yet the Milky Way has not been swallowed. Our galaxy continues to exist. Stars continue to orbit the galactic center. The Sun continues its own long journey around the center of the galaxy. We are not falling helplessly towards Sagittarius A star. The reason is distance. We are extremely far away from it. Gravity becomes dramatically stronger as you approach a black hole, but at large distances, the gravitational influence can be much more ordinary. A black hole can therefore exist in a galaxy without consuming everything around it. The same is true for smaller black holes. Imagine a black hole created from the collapse of a massive star. It might have several times the mass of the Sun. If another star passes at a safe distance, the two objects can orbit one another. Nothing has to fall into the black hole. The black hole can simply remain there, following the laws of gravity. The danger begins when an object gets too close. Then the situation changes. A star approaching a black hole can experience enormous tidal forces. Gas can be pulled from its surface. Material can spiral inward. The gas can form a hot accretion disk, and the region around the black hole can become intensely bright. This is one reason black holes can sometimes be easier to detect when they are actively feeding. The black hole itself remains dark. The material around it does not, and this gives us another interesting paradox. The most dangerous object in the region may also be surrounded by some of the brightest light in the universe. A black hole can be invisible while its surroundings shine brilliantly. Sometimes enormous jets of particles can also emerge from the regions around an actively feeding black hole. These jets can travel vast distances into space at speeds approaching the speed of light. They do not come from inside the event horizon. Nothing can escape from there. Instead, they are produced by extremely energetic processes in the material and magnetic fields outside the event horizon. This distinction is important because popular descriptions sometimes make it sound as though black holes are constantly shooting material back out after swallowing it. That is not what happens. The event horizon remains a one-way boundary. Anything that crosses it cannot return to the outside universe. The dramatic activity we observe comes from the environment around the black hole before material crosses that boundary. And this leads us to an even stranger question. If black holes can capture matter and nothing can escape from beyond the event horizon, does that mean black holes simply continue growing forever? At first glance, it might seem that way. A black hole can grow when it absorbs matter. It can gain mass when it captures gas, stars, or other black holes. When two black holes merge, their combined system can form a larger black hole. Over cosmic time, some black holes can become enormous. Supermassive black holes at the centers of galaxies can grow to millions or even billions of times the mass of our Sun. But even here, the story is not as simple as endless cosmic consumption. Black holes do not spend every moment feeding. Many are quiet. Some may have very little material nearby to consume. A black hole can sit in space for enormous periods of time without swallowing anything significant. And there is another remarkable process that we have not yet explored. Black holes may not be completely permanent. Quantum physics suggests that over incredibly long periods of time, black holes can slowly lose energy. This idea is known as Hawking radiation. It means that even black holes may have a beginning and an end. The process is extraordinarily slow for large black holes. A black hole with the mass of a star would take an unimaginably long time to evaporate. A supermassive black hole would take even longer, far longer than the current age of the universe. But the possibility changes the way we think about them. The black hole that once seemed like the ultimate symbol of permanence may actually be temporary on the longest possible timescales. So black holes are not simply cosmic monsters. They are part of the natural life of the universe. Some are born when massive stars die. Some grow through mergers and accretion. Some remain quiet for enormous stretches of time. And according to our current understanding of quantum physics, some may eventually disappear. Yet one mystery remains. If a black hole can eventually evaporate, what happens to everything that fell inside? Does the information about those objects disappear forever? Or is that information somehow preserved? This question became one of the deepest puzzles in modern physics. And it would force scientists to rethink what it really means for something to be lost. Because perhaps the strangest thing about a black hole is not that it can swallow matter. Perhaps the strangest thing is that it may challenge our understanding of information, time, and the very structure of reality itself. At the very center of our galaxy, hidden behind enormous clouds of dust and gas, something extraordinary is waiting. The Milky Way is not simply a collection of stars scattered randomly through space. It is a vast rotating galaxy containing hundreds of billions of stars, clouds of gas and dust, planets, and many other objects. All of these are moving through the galaxy as part of an enormous cosmic structure. And near the very center of that structure lies something we cannot see directly, a supermassive black hole. Its name is Sagittarius A star. Sagittarius, a star, is located about 26,000 light-years from Earth in the direction of the constellation Sagittarius. That distance may sound enormous, and it is. Light itself needs around 26,000 years to travel from the center of our galaxy to us. So when we observe Sagittarius A star today, we are not seeing the center of the Milky Way as it exists at this exact moment. We are seeing light and other signals that began their journey toward Earth thousands of years ago. The black hole itself is enormous by human standards. It has a mass of roughly 4 million suns. 4 million stars like our sun compressed into an incredibly small region. Yet despite this enormous mass, Sagittarius A star does not fill the center of the galaxy like some gigantic sphere. Its event horizon is relatively small compared with the enormous size of the Milky Way. The galaxy around it stretches across roughly 100,000 light-years. The black hole occupies only a tiny region at the center, and this gives us another reminder that black holes are not simply giant objects floating around swallowing everything in their path. Their gravitational influence reaches far beyond the event horizon, but the stars around the galactic center can still follow stable orbits. In fact, some of the best evidence for Sagittarius A star came from watching those stars move. Astronomers noticed that certain stars near the center of the Milky Way were moving incredibly quickly around a region that appeared to contain very little visible matter. One star in particular became extremely important. It is known as S2. S2 follows a highly elliptical orbit around the center of the galaxy. It completes one orbit in roughly 16 years. That may sound like a long time compared with a human life, but on the scale of the galaxy, it is remarkably fast. Astronomers have been able to track S2 and other nearby stars for decades. They watched them move across the sky. They measured their speeds. They calculated their orbits, and they discovered something extraordinary. Those stars were orbiting an invisible object with millions of times the mass of the Sun. There was no ordinary star cluster that could explain the observations. No visible collection of stars could remain packed into such a small region without behaving differently. The simplest explanation was a supermassive black hole, Sagittarius A star. The discovery did not come from seeing the black hole itself. It came from watching everything around it. Again, the invisible object revealed itself through gravity. This is one of the most beautiful ideas in astronomy. We cannot see the center directly, but we can watch the stars dance around it. Their movements tell us that something massive is there, something invisible, something compact, something powerful enough to control the orbits of stars moving at thousands of kilometers per second. And eventually, astronomers were able to get an even closer look. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star. It was not a traditional photograph of the black hole. Instead, it was an image created from observations of radio waves collected by telescopes around the world. The result showed a bright ring surrounding a dark central region. That dark region is called the black hole shadow. The shadow is created by the way the black hole bends light and captures radiation from the surrounding environment. The glowing ring comes from hot material and light near the black hole. The image may look simple, a bright circle, a dark center, but behind that image is an extraordinary amount of science. Telescopes located across Earth had to work together as though they were parts of one enormous Earth-sized telescope. The observations were combined and analyzed using sophisticated techniques. And after all that work, humanity received an image of the environment around the black hole at the center of our own galaxy. Something that had been invisible for centuries had finally left a recognizable signature. And yet Sagittarius, a star, is relatively quiet compared with some other supermassive black holes. It is not currently consuming enormous amounts of material. There is gas around it. There are stars nearby. There are powerful magnetic fields and energetic processes. But compared with some of the most active galactic centers in the universe, Sagittarius A star is fairly calm. That may be one reason we are able to live so far away from it without experiencing anything dramatic. Our sun is located roughly 26,000 light-years from the galactic center. At that distance, the black hole is not pulling our solar system inward. The sun follows its orbit around the center of the Milky Way, just as it has been doing for a very long time. One complete orbit takes the sun roughly 230 million years. That means the last time the sun was in approximately the same position in its galactic orbit, dinosaurs were not yet living on Earth in the form we know today. The galaxy itself moves slowly on this enormous scale. And at the center, Sagittarius A star remains quietly hidden. But Sagittarius A star is not unique. Once astronomers began understanding that supermassive black holes could exist at the centers of galaxies, another question appeared. How many galaxies have them? The answer seems to be many. In fact, observations suggest that most large galaxies contain a supermassive black hole at their center. These black holes can contain millions or even billions of times the mass of the sun. Some are far larger than Sagittarius A star. They are among the most massive individual objects known in the universe. And yet their story is still connected to the galaxies around them. A supermassive black hole does not simply sit at the center of a galaxy as an isolated object. Its history is deeply connected with the history of its galaxy. As galaxies grow, merge, and gather gas, their central black holes can grow as well. When enormous amounts of gas fall toward the center of a galaxy, some of that material can begin spiraling toward the black hole. It forms an accretion disk. The material becomes extremely hot. The disk can release enormous amounts of energy. And when this happens, the center of the galaxy can become brighter than all the stars around it combined. Astronomers call such an active galactic nucleus. Some of the most powerful examples are known as quasars. A quasar can shine so brightly that it can be detected from billions of light years away. The strange thing is that the energy does not come from the black hole itself. It comes from matter falling toward it. As gas spirals inward, gravitational energy is converted into heat and radiation. The result can be one of the brightest phenomena in the universe. A galaxy that might otherwise be difficult to see can suddenly have a brilliant central engine. And this tells us something important. A black hole can be dark, but the region around a feeding black hole can be extraordinarily bright. Some supermassive black holes also produce enormous jets. These jets are streams of highly energetic particles moving outward from the region around the black hole. They can extend for thousands or even millions of light years. They can reach far beyond the galaxy itself. Their origin is connected to the powerful magnetic fields and rotating material surrounding the black hole. The jets do not come from inside the event horizon. Nothing can escape from there. Instead, they form outside the horizon, where matter and magnetic fields are interacting in an extremely energetic environment. When we see one of these enormous jets stretching across space, we are seeing the influence of a black hole reaching far beyond its immediate surroundings. And this raises a deeper question. Why do these black holes exist at the centers of galaxies in the first place? Scientists are still investigating the full answer. Perhaps some began with the collapse of enormous stars in the early universe. Perhaps some formed from the direct collapse of massive clouds of gas. Perhaps smaller black holes merged together over cosmic time. Perhaps several of these processes contributed. The universe was very different when the first galaxies were forming. It was younger. It contained enormous amounts of gas. The first stars were appearing. Galaxies were colliding and growing. And somewhere inside those early galaxies, the first massive black holes were beginning their own long histories. Over billions of years, some of them grew enormously. They consumed gas. They merged with other black holes. They became central engines of galaxies. Some became quiet. Others became quasars so bright that their light traveled across most of the observable universe before eventually reaching Earth. And when we look at those distant quasars today, we are looking deep into the past. Some of the most powerful supermassive black holes we observe existed when the universe was only a fraction of its current age. This creates another mystery. How did some black holes become so massive so quickly in the early universe? We are still working on the answer. The more we study these objects, the more questions appear. And perhaps that is fitting, because a supermassive black hole is not simply a giant version of the black holes created by dying stars. It is part of a much larger story, the story of galaxies, the story of cosmic growth, the story of matter gathering under gravity across billions of years. And at the center of all of it, there can be a region where light disappears and space-time becomes profoundly distorted, a place that we cannot see directly, yet whose presence can shape the movement of stars across an entire galaxy. Sagittarius, a star, sits quietly at the heart of our own galaxy. It does not chase us. It does not call across the darkness. It simply remains there, a silent giant surrounded by hundreds of billions of stars. And perhaps the most remarkable part is that when we look toward it, we are not simply looking at a black hole. We are looking toward the center of our cosmic home, a place that has been there for an almost unimaginable length of time, long before humans existed, long before Earth had oceans, long before our sun was born. And as our journey continues, we can begin to look beyond the black holes at the centers of galaxies and toward an even stranger possibility. What happens when two of these enormous objects meet? When two black holes spiral toward each other through the darkness and finally become one? That collision does not simply create a larger black hole. It sends ripples through space-time itself. And for the first time, humanity has learned how to hear those ripples. There is a moment in the life of a black hole when even the darkness around it can become disturbed. It happens when two black holes find themselves trapped in a long and silent dance, circling one another through the emptiness of space. At first, the two objects may be separated by an enormous distance. Each black hole moves around the other, following the curved paths created by their combined gravity. From far away, the system may seem almost perfectly calm. There is no sound moving through the vacuum of space. No explosion can be heard. No bright flash necessarily announces what is coming, but something is happening. As the two black holes orbit one another, they disturb the structure of space-time itself. They send ripples outward in every direction. These ripples are called gravitational waves. The idea goes back to Einstein's general theory of relativity. If mass changes its motion in the right way, the geometry of space-time can carry a disturbance outward, much like ripples spreading across the surface of a quiet pond after a stone falls into the water. But there is an important difference. These are not waves moving through water. They are waves in space-time itself. As the black holes spiral closer together, they lose energy through gravitational radiation. Their orbit becomes smaller. They move faster. The dance begins to accelerate. The distance between them shrinks. The frequency of the gravitational waves increases. And eventually, after perhaps millions or billions of years of gradual orbital decay, the final moments arrive. The two black holes rush around each other at incredible speeds. Then they merge. For a brief moment, an enormous amount of energy is released in the form of gravitational waves. The two separate black holes become one larger black hole. The new black hole is initially disturbed, almost like a bell that has been struck. It begins to settle. The waves continue traveling outward. They cross the universe. They pass through galaxies. They pass through stars. They pass through planets. And eventually, perhaps billions of years after the original collision, they reach Earth. But by the time they arrive, they are incredibly weak. The amount by which space-time stretches and compresses can be unimaginably tiny. This created an extraordinary challenge. How could humans possibly detect something so faint? For decades, scientists worked toward an answer. The solution was LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO uses enormous instruments with long, perpendicular arms. Laser light travels down these arms and reflects from mirrors before returning. The system is designed to measure incredibly tiny changes in distance. When a gravitational wave passes through Earth, Spacetime itself stretches slightly in one direction and compresses slightly in another. The distances measured by the detectors change by an almost unbelievably small amount. LIGO was built to detect that change, and in 2015, something extraordinary happened. The detectors recorded a signal. It lasted only a fraction of a second. But inside that brief signal was the evidence of two black holes colliding more than 1 billion light years away. The event was later named GW150914. For the first time, humanity had directly detected gravitational waves. We were no longer limited to seeing the universe through light. We had begun to listen to it through gravity. The discovery was historic. For centuries, astronomy had depended largely on light. Visible light, radio waves, infrared radiation, X-rays, gamma rays. All of these forms of electromagnetic radiation carry information across the universe. But gravitational waves gave us an entirely new way of observing reality. They carried information about objects that could be almost completely dark. Two black holes can collide without producing the kind of bright, visible explosion we might expect from ordinary stars. But the movement of their enormous masses leaves a signature in space-time, and that signature can travel across the universe. When the first signal was detected, scientists could reconstruct the final moments of the collision. The signal increased in frequency as the black holes spiraled closer. Then came the merger. Then the newly formed black hole settled down. The shape of the signal contained information about the masses and motion of the black holes. In a sense, the collision had written its own story into the fabric of space-time, and humanity had learned how to read it. Since that first detection, many more gravitational wave events have been observed. Black holes have merged. Neutron stars have collided. The universe has become a much more active place when we learn how to listen for its hidden signals. Every detection gives scientists another piece of information about the population of black holes scattered throughout the cosmos. Some are more massive than expected. Some are spinning rapidly. Some formed in environments we do not fully understand. And each collision tells us something about the evolution of the universe. There is something deeply beautiful about the idea. A collision that happened billions of years ago can still reach us today. The black holes are long gone from that particular moment. The galaxies around them may have changed. Stars may have been born and died. Planets may have formed. But the gravitational waves continued traveling outward, and eventually they arrived here, on Earth, in a carefully constructed instrument. A tiny movement in a laser beam became evidence of one of the most violent events in the universe. The universe had been speaking in gravity for billions of years. We had only just learned how to listen. And while gravitational waves gave us a new way to detect black holes, another breakthrough was waiting. For decades, scientists had known that black holes should have a dark shadow surrounded by light from the material near them. But knowing what something should look like is very different from actually seeing it. Then, in 2019, humanity saw something that had once seemed impossible. The first image of a black hole. The image did not look like a photograph from a science fiction movie. There was no perfect black sphere floating against a field of stars. Instead, there was a glowing ring of light surrounding a dark center. It was blurry. It was simple. And yet it represented one of the most extraordinary achievements in the history of astronomy. The object was located in the center of the galaxy Messier 87 often called M87. M87 is a massive elliptical galaxy located about 55 million light years from Earth. At its center is a supermassive black hole with a mass billions of times greater than that of the Sun. The black hole is known as M87 star. The image was released in April 2019 by the Event Horizon Telescope collaboration. But what exactly were we looking at? Not the black hole itself. The central dark region is the black hole's shadow. Around it is a ring of glowing material. That light comes from extremely hot gas and plasma surrounding the black hole. The enormous gravitational field bends the light around the black hole. Some of the light that would normally travel in a straight path is forced into curved trajectories. This creates the bright ring surrounding the dark central region. The shape and size of the shadow are related to the mass of the black hole and the way spacetime behaves around it. And that is what made the image so important. It was not simply a picture. It was a test of our understanding of gravity. Einstein's theory had predicted that massive objects would bend spacetime and therefore bend light. The image of M87 star provided an extraordinary visual confirmation of what those equations had suggested. But creating the image was anything but simple. The Event Horizon Telescope is not one ordinary telescope. It is a network of radio telescopes located around the world. They work together using a technique called very long baseline interferometry. The basic idea is remarkably clever. Instead of building one telescope as large as Earth, astronomers use telescopes separated by enormous distances and combine their observations. The Earth itself becomes part of the experiment. Observations were collected from locations around the planet. The telescopes recorded radio signals from the region around M87 star at extremely high precision. Those observations were then combined using sophisticated computer processing. The amount of data was enormous. Hard drives containing the observations had to be physically transporting because the data volumes were too large to simply send across the internet at the time. Scientists then spent months and years processing and checking the information. Different teams worked independently. They compared their results. They tested whether the structure they were seeing could be explained by noise or instrumental errors. Again and again, the same basic ring-like structure appeared, and eventually the image was ready. A dark center, a glowing ring, a shape that represented a region more than 50 million light years away. For many people, the image became the face of the black hole, but its importance went far beyond the picture itself. For the first time, humans had directly observed the immediate environment surrounding the shadow of a black hole. Something that had existed only in equations, simulations, and indirect observations had become visible. The image also gave scientists a way to compare observations with predictions. General relativity had made very specific predictions about the appearance of a black hole's shadow. The observed structure was consistent with those predictions. This did not mean that every mystery had been solved. Far from it. The image answered some questions while creating others. We still do not know exactly what happens at the deepest interior of a black hole. We still do not have a complete theory that combines general relativity with quantum mechanics. We still do not fully understand how the largest black holes formed so quickly in the early universe. And we still do not know exactly what happens to information that crosses the event horizon. The photograph did not show us the inside. It showed us the boundary between what can be observed and what remains hidden. And perhaps that is why the image is so powerful. When you look at that dark center, you are looking at something that light cannot escape from. You are seeing the shadow of a region where our ordinary ideas about space and time begin to break down. The image traveled around the world. People who had never studied relativity could suddenly look at the same dark ring that astronomers had spent decades trying to observe. A prediction from Einstein's equations had become something we could see. And just a few years later, another remarkable achievement would follow. Astronomers would turn their attention toward the black hole at the center of our own galaxy, Sagittarius A star. For the first time, the darkness at the heart of the Milky Way would also begin to take shape. And once again, we would be reminded that the universe can hide its most extreme objects in darkness while still leaving traces of them everywhere around us. When we talk about black holes, one of the strangest things we have to reconsider is time itself. In everyday life, time feels simple. A minute is a minute. An hour is an hour. A clock on your wall seems to tick at the same steady rhythm as every other clock. But according to Einstein's theory of relativity, time is not completely separate from space. It is part of something called spacetime, and gravity can change how time passes. The stronger the gravitational field, the greater the difference can become between clocks in different places. Near a black hole, this effect becomes extreme. Imagine two identical clocks. One remains far away from the black hole. The other travels toward it. From the perspective of the distant clock, the clock approaching the black hole appears to tick more slowly. As the falling clock gets closer to the event horizon, the difference becomes greater. The light carrying information from the falling clock also becomes increasingly stretched. Its frequency decreases. Its color shifts toward the red end of the spectrum. The signal becomes weaker. And eventually, from the distant observer's point of view, the falling object appears to slow almost to a stop near the event horizon. This is where the popular idea comes from that time stops at a black hole. But this statement needs to be handled carefully. Time does not simply stop for the person falling into the black hole. From the falling person's own perspective, their clock continues to work normally. Their heartbeat continues. Their thoughts continue. Their watch continues ticking. If they are falling toward a sufficiently large black hole, they could cross the event horizon without seeing their own clock suddenly freeze. They would continue inward. The strange difference appears when we compare their clock with a clock belonging to someone far away. The distant observer and the falling observer do not experience the journey in the same way. This is one of the central ideas of relativity. There is no single universal clock governing the entire universe. Different observers can measure time differently depending on their motion and their position in a gravitational field. We can already measure much smaller versions of this effect around Earth. Satellites experience different gravitational conditions from clocks on the ground. Modern navigation systems have to account for these differences. Without corrections based on relativity, their calculations would gradually become inaccurate. Near a black hole, however, the effect becomes much stronger. The closer you move toward the event horizon, the more dramatic the difference can become. And this creates a beautiful but confusing picture. From far away, it can look as though the falling object is becoming frozen. From the falling object's own perspective, There is no sudden freezing. Both descriptions can be correct because they refer to different observations and different paths through space-time. The black hole does not simply stop time. It changes the relationship between time and space. And once we understand that, another question begins to appear. If something crosses the event horizon and can never return, what happens to the information carried by that object? Imagine that a book falls into a black hole. The book contains information. The arrangement of its atoms contains information. The letters printed on its pages contain information. Even the microscopic state of every particle carries information about the object. Once the book crosses the event horizon, an outside observer can no longer receive information directly from it. The book is gone from the observable universe outside the black hole. But does the information itself disappear? This question became one of the deepest puzzles in modern physics. It is known as the black hole information paradox. The problem comes from the tension between two powerful ideas. Quantum mechanics tells us that information about a physical system should not simply disappear. But classical general relativity appears to allow information to pass beyond the event horizon and become permanently inaccessible. At first, this may sound like a philosophical question, but it is actually a serious problem for physics. Information is not simply a collection of words or numbers. In quantum physics, information describes the physical state of a system. If that information were truly destroyed, it would challenge some of the fundamental principles of quantum theory. So imagine again that the book falls into the black hole. From the outside, we cannot retrieve it. We cannot open the pages. We cannot look inside. We cannot receive a message from beyond the event horizon. But perhaps the information has not been destroyed. Perhaps it has been transformed. Perhaps it has somehow become encoded in the black hole itself. Or perhaps it is connected to the radiation emitted by the black hole. This is where the story becomes even stranger. For a long time, black holes were thought to be completely black. Nothing could escape. They could absorb matter and energy, but they would never give anything back. Then, in the 1970s, physicist Stephen Hawking discovered something remarkable. When quantum mechanics is taken into account near the event horizon, black holes are not completely black. They can emit radiation. This radiation became known as Hawking radiation. The idea begins with quantum fields. Even what we think of as empty space is not truly empty. At the quantum level, fields exist throughout space. They can fluctuate. Particles can appear and disappear as part of the behavior of these fields. Near an event horizon, the extreme structure of spacetime creates a situation where quantum effects can lead to radiation escaping to the outside universe. The popular explanation often describes pairs of particles appearing near the horizon, with one falling into the black hole while the other escapes. This picture can be useful as an introduction, although the actual physics is more subtle than this simple story suggests. The important result is that the black hole can lose energy, and because energy and mass are connected, losing energy means losing mass. The black hole can slowly become smaller. This is extraordinary. A black hole that once seemed like the ultimate permanent object may actually have a finite lifetime, but the process is incredibly slow for large black holes. For a black hole with the mass of our Sun, the evaporation time would be unimaginably longer than the current age of the universe. A supermassive black hole would take even longer. So there is no reason to expect Sagittarius A star to disappear anytime soon. The universe is far too young for that process to have become important for large black holes. But as the black hole loses mass, something interesting happens. A smaller black hole is hotter than a larger one. A hotter black hole emits radiation more rapidly. As it loses more mass, it becomes even hotter. As it becomes hotter, it loses mass even faster. The process can therefore accelerate toward the end. Eventually, according to the simplest picture, a small black hole could enter its final stage of evaporation. Exactly what happens during that final moment is still unknown. Our current theories become incomplete when quantum gravity becomes essential. Perhaps the black hole disappears completely. Perhaps a tiny remnant remains. Perhaps something more complicated happens. We do not yet know, and Hawking radiation brings us back to the information paradox. If a black hole slowly evaporates and eventually disappears, what happens to all the information about everything that fell into it? Imagine the book again. It falls into the black hole. The black hole grows slightly. Millions or billions of years pass. The black hole emits Hawking radiation. Eventually, the black hole becomes smaller, and perhaps one day it disappears. But if the information inside was truly destroyed, then the universe has lost information forever. Quantum mechanics strongly suggests that this should not happen. So where is the information? Perhaps the radiation contains it. But if Hawking radiation is completely random, then it does not appear to carry enough information to reconstruct what fell inside. This is the heart of the paradox. Something went in. The black hole eventually disappears, and physics seems to demand that the information must still exist somewhere. Scientists have proposed many possible solutions. One idea is that the information is encoded in the radiation in an extremely subtle way. Another possibility is that information is somehow stored at the boundary of the black hole. This has led to profound ideas about the relationship between information and the surface area of a region of space. The holographic principle is one of the most fascinating developments connected to this problem. It suggests, in a broad sense, that information describing a volume of space might be represented by information associated with its boundary. This is a strange idea. It suggests that the amount of information contained within a region may be related not to its volume, but to its surface area. Black holes played an important role in developing this way of thinking. The idea has changed the way many physicists think about space, gravity, and information. Perhaps space itself is not as fundamental as it appears. Perhaps space-time emerges from deeper quantum relationships. Perhaps gravity is connected to information in ways we are only beginning to understand. These are not settled answers. They are active areas of research. And this is what makes black holes so valuable to science. They are not simply objects we observe from a distance. They are theoretical laboratories where our deepest theories meet. Gravity meets quantum mechanics. Space meets time. Matter meets information. And the boundary between what we know and what we do not know becomes unusually clear. The story of Hawking radiation also changes the meaning of the word black. A black hole may appear completely dark because light cannot escape from beyond its event horizon. But the black hole as a quantum object is not perfectly silent. It can slowly release energy. It can slowly lose mass. And on unimaginably long timescales, it may eventually disappear. This means that even the darkest objects in the universe may have a life cycle. They can be born, they can grow, they can interact with their surroundings, they can merge, and perhaps, after an almost unimaginable amount of time, they can fade away. The universe itself is still very young compared with these timescales. Stars are still forming, galaxies are still merging, black holes are still growing. The great era of black hole evaporation lies unimaginably far in the future. And yet, by thinking about that distant future, we learn something about the universe today. We learn that black holes are not simple cosmic traps. They are places where our understanding of reality is tested from almost every direction. They challenge our ideas about time. They challenge our ideas about information. They challenge our understanding of gravity. And they may eventually help us discover how gravity and quantum physics fit together. Perhaps one day, a more complete theory will explain exactly what happens to information when matter disappears beyond an event horizon. Perhaps it will explain what lies at the center of a black hole. Perhaps it will even reveal that some of the things we currently think are fundamental are actually emerging from something deeper. For now, we can only follow the evidence. We can observe the stars moving around invisible masses. We can detect gravitational waves from distant mergers. We can photograph the shadows of supermassive black holes. We can measure the effects of gravity on time. And we can use the mathematics of quantum physics to predict that black holes may slowly evaporate. But the deepest secrets remain hidden. And perhaps that is exactly where our journey should continue. Because if black holes can change our understanding of time and information, then there is one final question that becomes almost impossible to ignore. What do black holes tell us about the universe itself? And what might they reveal about the ultimate fate of everything that exists? By now, we have traveled a long way into the darkness. We have followed massive stars through their final moments, watched black holes bend light, imagined the strange passage through an event horizon, and explored the mysterious relationship between gravity, time, and information. But once we begin thinking about black holes, another possibility naturally appears. Could they somehow be connected to other places in the universe? This is where the idea of wormholes enters the story. A wormhole is a hypothetical structure that could, in theory, connect two distant regions of space-time. Instead of traveling across an enormous distance through ordinary space, a traveler might imagine taking a shortcut through a kind of tunnel. The simplest way to picture it is to imagine a sheet of paper. Place 2 points far apart on the sheet. Normally, traveling from one point to the other means crossing the entire distance between them. But if you bend the paper until the 2 points become close together, you could imagine a tunnel connecting them. The distance through the tunnel would be much shorter than the distance across the surface. This is only an analogy, but it gives us a simple way to imagine what a wormhole might do. The interesting part is that wormholes are not completely outside the mathematics of physics. Certain solutions to Einstein's equations allow structures that resemble wormholes. One of the earliest examples is associated with Einstein and physicist Nathan Rosen. Their mathematical construction became known as an Einstein-Rosen bridge. But there is a major problem. A mathematical possibility is not the same thing as a physical object that exists in nature. The wormholes described by simple versions of general relativity are not necessarily stable. They could collapse too quickly for anything to travel through them. To keep a wormhole open, some models require unusual forms of matter or energy with properties that have never been demonstrated on the necessary scale. This is where the boundary between science and speculation becomes important. Science fiction often presents wormholes as if they were natural tunnels waiting to be discovered. We could enter one near a black hole, travel through darkness, and emerge somewhere millions of light years away. It is a beautiful idea, but we have never observed a traversable wormhole. There is currently no confirmed evidence that they exist. So when we talk about wormholes, we have to separate what physics allows mathematically from what nature has actually shown us. Black holes themselves are very different. We have overwhelming observational evidence that black holes exist. We have watched stars orbit invisible massive objects. We have detected gravitational waves from merging black holes. We have observed the hot material surrounding them, and we have even produced images of the shadows of supermassive black holes. Wormholes remain hypothetical. This distinction may seem small, but it is one of the most important habits in science. A fascinating possibility can be worth exploring even when we do not yet know whether nature has realized it. Ideas can lead to new questions. New questions can lead to new experiments. And sometimes a strange mathematical possibility eventually becomes an important part of our understanding of nature. But sometimes it remains only a possibility. There are other mysteries surrounding black holes as well. Could black holes be connected to the earliest moments of the universe? Could tiny black holes have formed shortly after the Big Bang? Could some of these primordial black holes still exist today? Could they make up part of the mysterious dark matter that appears to influence galaxies? These questions have been studied seriously. But once again, we must be careful. Dark matter has strong observational evidence. We know that something is influencing the motion of galaxies and the growth of large-scale cosmic structures. But we do not yet know exactly what dark matter is. Primordial black holes are one possible explanation for some of the dark matter under certain conditions, but they have not been established as the answer. The universe often gives us clues without giving us the complete solution, and perhaps this is why black holes are so captivating. They sit at the meeting point between what we can observe and what we can only imagine. They are real objects, but they contain regions that we cannot directly explore. They can be described by equations, but those equations may eventually stop giving us a complete answer. They can be photographed indirectly, but the deepest interior remains hidden. They can merge and send gravitational waves across the universe. They can slowly lose energy through Hawking radiation. And they may even help us understand the relationship between space, time, gravity, and information. Yet after all these discoveries, there are still questions waiting in the darkness. Perhaps that is the most appropriate place to end our journey. Not with a final answer, but with the quiet realization that the universe is still much larger than our understanding of it. Tonight, we began with a simple question. What is a black hole? We discovered that it is not really a hole in the ordinary sense. It is a region of space-time where gravity becomes so extreme that beyond a certain boundary, escape is no longer possible. We followed the final moments of massive stars as their cores collapsed under gravity. We imagined the formation of an event horizon. We watched light bend around invisible objects. We explored what might happen to a traveler falling inward. We learned about tidal forces and the strange process known as spaghettification. We traveled to the center of the Milky Way and met Sagittarius A star, the supermassive black hole at the heart of our galaxy. We looked outward toward the enormous black holes that live at the centers of distant galaxies. We imagined two black holes spiraling toward one another and finally merging, sending ripples through space-time itself. We listened for those ripples through gravitational wave detectors, and we looked at something that once seemed impossible: the first image of a black hole. A glowing ring, a dark center, a shadow created by gravity itself. Then we went deeper. We asked what time means near a black hole. We wondered whether information can truly disappear. We explored Hawking radiation and the possibility that black holes may eventually evaporate. And finally, we allowed ourselves to imagine possibilities beyond what has been confirmed. Wormholes, primordial black holes, unknown forms of matter, unknown structures hidden deep inside space-time. Some of these ideas may eventually lead to discoveries. Others may remain beautiful possibilities, and that is okay. Science does not become weaker because it admits what it does not know. In fact, one of the most powerful things science can say is simply this: we do not know yet. The darkness beyond the event horizon reminds us of that. There are places in the universe that light cannot return from. There are questions that our instruments cannot yet answer. There are mathematical ideas that we have not yet learned how to connect to reality. And somewhere in that enormous darkness, the next discovery may already be waiting. Perhaps future generations will understand what happens at the center of a black hole. Perhaps they will solve the information paradox. Perhaps they will discover what dark matter really is. Perhaps they will find that wormholes are impossible. Or perhaps they will discover that nature is stranger than we ever imagined. For now, we can simply look upward. The night sky above us is filled with stars. Some of those stars will one day disappear into darkness. Some may leave behind black holes. Some black holes may eventually merge. Some may slowly fade away over unimaginable stretches of time. And through all of it, the universe continues its quiet journey. So as you let your thoughts become softer tonight, you do not need to solve any of these mysteries. You do not need to understand every equation. You do not need to find the answer to what lies beyond the darkness. You can simply let the ideas drift away. Imagine the distant stars. Imagine the silent galaxies. Imagine Sagittarius A star resting quietly at the center of our own cosmic home. Imagine two distant black holes circling one another through the darkness. Imagine the faintest ripple traveling across space-time until, billions of years later, it reaches a tiny planet around an ordinary star. And imagine that for just a moment you are here to notice it. The universe is vast. Much of it remains unknown. And somehow, in the middle of all that darkness, we have learned to look. We have learned to listen. We have learned to ask questions. And perhaps that is enough for tonight. Thank you for spending this quiet time with me and for allowing mysterious, sleepy history to be your night companion. If this journey helped you relax or simply gave your mind something peaceful to wander through, take a moment to like the video and subscribe. It helps our little group grow and allows us to continue making these quiet journeys together. And before you drift away, I would love to know where you are listening from tonight. Tell me the place you are in and your local time in the comments. It is always wonderful to imagine how many different corners of the world are sharing the same quiet night together. Now let the stars become distant. Let the questions become quiet. And let the darkness of space slowly fade into the darkness behind your eyes. There is nothing left to solve tonight. The universe will still be here tomorrow. For now, you can simply rest. Thank you for joining me on tonight's journey through the deepest mysteries of black holes. Sleep well, and I'll see you in the next journey through history.